Could you be able to get it?
Yes, sir. They have to just enable it seems.
Okay. You have to call up that guys?
I'm sorry, sir.
Do you have to call up those people and enable? Ask them to enable?
Ye- Yes, they are online with me on WhatsApp.
Okay. So you can ask them to.
Yes, we are live. Uh, one, one small speed 10 seconds. Sorry, sir.
Do you have to call up those people and enable?
So we are live now.
Okay. Well, yeah, good evening to all of you. Well, I think you might have gone through the lectures, and I do hope that these lectures were useful to you. The purpose of today's live session is to clarify any questions that you may have whenever you went through these recorded classes. So if any of you wish to ask any questions, please feel free to ask. Or you can also send the questions in the chat box, right? Or maybe in the question and answers, so that I could able to address your questions. Can the participants speak also, or they can send only the questions?
They cannot speak, sir. It's a one-way
Okay.
interaction.
Okay, no problem. So we do not know, right? How many people are there, or if at all anyone is there.
Yes, there are 6 people watching it live. We
Okay.
also sent out a Google form earlier in case if they had any queries, but we do not have any questions as of now.
Okay.
We are in week 3 of our content, where we are studying about passivity, mixed potential theory, DC polarization experiments.
So that means there must be a fair idea about the thermodynamics of electrochemical reactions, especially determining the equilibrium potentials using the Nernst equation. And of course, they should also be knowing the relation between the free energy change, gives free energy change, and the electrode potentials. Right. They also should be knowing by this time that how to calculate the equilibrium potentials, and then from there to determine whether a given metal can corrode uh, the given environment. Okay. But that's about knowing how to determine if a metal will undergo corrosion. Subsequently, I think the lectures were focused on the electrochemical kinetics, and more specifically related to the corrosion, right? So there the relation between the overall voltage and the resulting current, and also how to determine you know like the corrosion potentials and the corrosion current densities, right? So we also would have seen what happens if the metal passivates, how does the anodic polarization curve especially reveal the passivation of a given metal, right? So the parameters such as passive current density, passive potentials, heating potentials, and these are the indications of the tendency of the metal to show passivity, and how these parameters also indicate the relative passivity of a given metal. Well, I just look forward to any questions any of you have. Please do send it through the chat box. I'll be more than happy to address those questions. And the chat box, they are allowed, right? I think.
Yes, sir, they are allowed. Around 5 people have joined the live session now.
Okay. So there are no questions?
Until now, there isn't, sir.
I think we have also completed a few assignments, right? I think.
Yes, they have.
So is any of you have any questions on the assignments? Yeah, looks like everything's clear. Yeah. No, actually, what I would advise, I mean, those who have joined now, advice is we are going to have in total 3 live sessions. Today is 1, 2 more we have. Please do come out with any questions that you have in mind. I'm sure that, the recorded classroom lectures may not be as effective as your in-person teaching, right? So, yeah, if you have any questions, anything that you don't understand, that it bothers you, I think you should note it down, and it's a time to get them clarified. Of course, I mean, the TA, I think we have Ms. Kirtia Ganeshan, who is helping you to address any questions that you may have even before we have live sessions. So feel free to ask questions. I mean, this is very important. And more so, we don't have much chance to interact with you, personally. So, okay, apart from live sessions, we may have it next time. You do send your questions to the email that is given. I think I myself and Keithiga would be very, very happy to respond to you. Yeah, so of course, if there are no questions, I would like to close it up. So we have a couple of minutes now. I'll wait for your questions. And if you feel that there is nothing that you'd like to ask now, then we can close it in about a few minutes, couple of minutes.
Sir, there is a question.
Yeah, please.
Vilas Kulkarni asks that, sir, I see you mentioned no sign convention for E cell, but many references use sign convention.
Yeah.
So
Well,
that's
it's a good question. Okay. Well, I suppose you understand what is meant by electrode potential and what is meant by equilibrium potentials, right? The equilibrium potential is the one that the electrode establishes in relation to the solution when the electrode material and its ions are present in the solution, right? So for example, zinc is immersed in zinc ions. You will get a electrode potentials are called as equilibrium potential, right? And if the concentration of zinc ions or the concentration is unity, then the potential of that equilibrium measured with respect to standard hydrogen electrode is called as the standard potential, right? Now, this is sign invariant, right? So when you say sign invariant, what it really means is it doesn't refer either to a reduction potential or to an oxidation potential. In the olden days, people used to call as reduction potentials, which is the European convention, and in oxidation potential, it is an American convention. Now, what does it mean oxidation? You write zinc, going to zinc 2 plus 2 electron. You write equation that way. The potential so established is called as the oxidation potentials. On the other hand, if you write equation zinc 2 plus 2 electron gives you zinc, it is called as reduction potentials. The problem over there is that it does not recognize that we are talking about an equilibrium potential. There is neither oxidation nor reduction. The zinc ions will deposit on the zinc surface and zinc metal will dissolve and form zinc ions in solution. So the rate of zinc getting oxidized to zinc 2 plus and the rate of zinc 2 plus getting reduced to zinc, both are same. So that means they are in absolute equilibrium. At that condition, if you can measure the potential of that interface with respect to a standard hydrogen electrode, I suppose you understand what a standard electrode is. That means you can say typically you have platinum wire metal immersed in an acid solution of activity 1, and the hydrogen partial pressure over there is about 1 atmosphere. So if you connect these two electrodes, the zinc electrode and hydrogen electrode, and measure the potential using a very high impedance voltmeter or by using a potentiometer, wherein zinc is still in equilibrium, hydrogen also is in equilibrium, the potential so measured is called as equilibrium potentials. So this is given by Dinner's equation, right? E equal to E naught plus RT ln F and logarithm of oxidant upon the logarithm of reductants, right? This is what is given there. So that equation will give you a potential which is equal to what is measured. So this is called as electrode potentials. Now let's come to cell potential, right? What is the cell potential? Cell is formed if you have two electrodes and of different kind, you connect them. For example, you may have zinc in equilibrium with zinc ions and copper in equilibrium with copper ions. You just sort them together, you would have a cell. A cell has a potential and also passes the current. Now the cell potential always will be positive, no matter which two metals you are going to get, because E cell is equal to E cathode minus E anode. So one of them will turn into a cathode, other will turn into anode. So you always get like a dry cell battery, any batteries of any kind, cadmium nickel batteries, you always get a positive potential. So it does not depend on a sign, actually. I don't know what you mean that. So the cell potential is always positive, and then only cell will operate. Okay, so that is no problem. We don't even, nobody talks about sign convention for an electrochemical cell, because electrochemical cell will always see a positive potential. Okay. Okay. On the other hand, the confusion many times happens is with respect to the equilibrium potentials, okay, which I have explained to you why we consider that the equilibrium potential is sign invariant, because this neither oxidation nor reduction, both are happening at the same rate at the surface, right? When both are happening at the same rate at the surface, why would you call oxidation? Why would you call reduction? Right? You don't call it. So that is why it is called as equilibrium potentials. Okay. So that's the kind of answer for that. Okay. I hope that is that clarifies your question. If you're not, please do let me know.
He just commented that Vilas got confused with different forms of Nernst equations. Like, I think what he was trying to ask about is the sign convention that we follow in Nernst equations. How is it sign invariant?
No, see, that is why we normally, well, I don't have. Say, for example, we say zinc here, you write zinc 2 plus 2 electrons and is equal to zinc. Okay, so this is equilibrium. So whenever you represent equilibrium, you please write the oxidant on the left side, reductants on the right side. Okay, then you write this equation E, right, isn't it? Is equal to E naught plus again 2.303 T by NF logarithm of that. So now the logarithm of this, what happens? This comes here, right? Isn't it? In 2 plus, oops, what happened? Hello?
Yes, sir.
Yeah, I'm sorry. I mean, okay, I missed the board. No, yeah.
Okay.
Oops. Okay, so zinc upon zinc. So if you write like that, you'll never get a wrong one. Please notice this, what you're seeing here in the literature is in equilibrium potentials, right? For zinc, it's always going to be minus 0.763. Okay. Now, if this is the value, okay, then automatically this comes here. So you have to put this only here. So yeah, there are books, which are given, and there are some shortcuts. They always do it. I think that is absolutely wrong. Okay, that cannot be given. Okay. Well, what do you say? If I can go to next page, can I go next page?
Yes, sir. Like on the right hand side, or you can scroll it down.
Okay, thank you. See, the problem is like this. People find a convenient way of doing it, right? People, for example, reverse equation and add it, okay? You know, for example, the people might say, write like this. Okay. And then people write zinc, let's say 2 plus. They simply add these two, okay? And they write this oxidation potential here, reduction potential here, and they add it together, then they get E cell, right? This is absolutely wrong, right? Why it is wrong? Because first of all, we do know what it is. How do you know that this is the oxidation? How do you know this is the active metal? How do you know this is noble one? Suppose I give you, let's say, a metal M and another one, a redox system OX plus N electron, giving this. If I give a potential 1 and potential 2, how will you decide which is oxidation, which is reduction? You don't know. Just because you know zinc, you are able to do it. But if you don't know what these are, you can't find out. So the problem is that the shortcut, okay? And if you go further and further, later when you talk about polarization, okay, you see that in the polarization, you see that I will able to carry out oxidation and reduction without changing conversion. Let me tell you what it is, okay? Let me go here now, okay? Let's take this reaction, zinc 2 plus. Okay. Okay. Suppose the potential is minus 0.76 volt, right? This is standard state. Now, suppose I apply I change the potential of this, let's say to minus 0.773 volts. Okay. Or I change it to minus 0.7, say 5.3 volts. Okay. Suppose say this. Now, please see the potential of this is changed from minus 0.76 to 773. This, now what will happen here? Here you will get this. What about here? Here you will get okay. So you see now, I have not changed the sign, right? Without changing the sign, I kept the sign negative. Even then, at this particular potential, you'll find zinc gets oxidized. I don't have to make plus 0.763 to say the metal is corroding, metal is getting oxidized. No. So it is scientifically incorrect to say that only at 0.76 the metal get oxidized. No. The metal can get oxidized even when it is slightly above this, and a potential above this, and that is why we call them as over voltage, eta, right? You will see this concept in the kinetic diagram. It is eta which decides, okay, whether there will be oxidation or reduction. The potential, what you talk about, equilibrium potential, it does not decide. So if you are going to say reduction potential, it's already reducing. Your oxidation potential is already oxidizing. So so you don't need to go to plus 0.76 to get oxidized. It is enough to go little above this voltage, get oxidized. Little below this, it will become reduced. Okay. So this is the concept you need to follow in order to understand the over voltage. Okay. The over voltage is a consequence of this. If you don't follow this, you can't really understand the over voltage. Okay. So I hope that you got the point, and otherwise you do let me know. I will try to see how I can explain to you better. You please send it to the chat box if you still you are not clear about it.
Thank you, sir, for
Thank you.
getting his question. So a couple more, like 2 more comments and 1 question we have.
Okay.
And Ajay Dua and Ishika Khatri, both of you have asked about the solution to the assignment, and you'll get it. It will be available on the portal tomorrow, and it has all the detailed steps of each questions. And if you are still having doubts after seeing the solutions, you can please feel free to email us. We will be able to get more insights on that. And Ishika Khatri asks, when we use limiting current density and difference between exchange current density and limiting current density. That's a question, sir.
Yeah, it's again very, very interesting question. Okay. Let's now look at some metal. Let's take, let's say zinc only. Okay. I just immerse zinc in solution here. Okay. Okay. So zinc ions. I said when they are equilibrium, I said the rate of oxidation is equal to rate of reduction. That is why we call them as equilibrium potential, right? Isn't it? So that is, zinc is getting oxidized. See, in this case, zinc is getting oxidized as zinc 2 plus and 2 electrons. And this is what this one here, zinc is ions are getting reduced as zinc. Now look at this. It is happening at this interface, right? When zinc is getting oxidized as zinc ions, what happens? Please see, zinc ions move in the direction, right? If this move in the direction, the current flows in the direction of movement of positive charges, right? If positive charges moves in the direction, then that is the direction current is moving. The current moves in the opposite direction of negative charges movement. So in this case, current is moving like that. So now look at the other reaction. Suppose you have zinc 2 plus. It moves and gets electrons. Now the current is moving opposite direction. Because the rate of this reaction is equal, there is no net current. But there is a rate at which this reaction is occurring. That's the rate at which this reaction is occurring, right? Now, what is the mean? Now let's look at rate of reaction. Rate of reaction are given as R, rate of reaction, is given in terms of, isn't it, moles right, per area per time. Please look at this many moles of zinc 2 plus is getting oxidized. This many moles of zinc 2 plus is getting reduced. That means current is moving forward and backward. It is getting exchanged on the interface. Now, let's look at this. Now, this is the rate of reaction. What is the corresponding current? The corresponding current, you have to multiply this rate of reaction, or moles is equal to what? Number of electrons into the Faraday gives you current, which is called exchange current. Look at this. I use the term I naught because this represents a state where the current is moving back and forth, but there's no net current. End of the day, there's no net oxidation, no net reduction, right? Now you see the relation between these two. So this is called exchange current density because it is getting exchanged here and no net reaction, right? Now let me go to the diffusion one, right? Now let me take this reaction. Let's say I have platinum here. I have taken a beaker and I have, let's say, some water or sodium chloride, whatever. Maybe I have some water. Okay. Now it has got some dissolved oxygen content. Here is dissolved oxygen. You know amount of dissolved oxygen normally in the water? It is in the range of 6 to 8 ppm. Okay. Now you have an equilibrium here. What is the equilibrium here? The equilibrium here is oxygen plus water and plus 4 electron gives you 4 OH minus. Okay. Okay. Now what happens? At this surface, one-way reaction is reducing oxygen there. The other reaction is OH minus is tending to become oxygen there. So in this case, this is the equilibrium that's happening, and there is a corresponding E naught for that. Okay, you can find out from the the standard table, what is that value? Now, this is an equilibrium now. Now I want to have a reduction reaction. What is reduction reaction? Now let's say oxygen plus water plus 4 electrons comes now 4 OH minus. Please again remember over voltage. This is equilibrium now. If I have to do this, then the over voltage has to be negative. Am I right? You have to go back and see. The over voltage has to be negative. In order that this reaction occurs. If the over voltage is positive, for example, if the voltage is positive, okay, then what happens? Then you will have oxidation reaction. Okay. So when you have negative, it happens now. Now, if this is what is happening, okay, now how does the reaction occurs in relation to over voltage, right? So I'm going to take the next page. Okay. Now, if I plot how the current is changing, or current density is changing with respect to the applied potentials. Please look at, I have equilibrium potential somewhere here. This is equilibrium potential here. This is equilibrium potential. This is the exchange current density. Am I right? I naught. The value here. And this is the equilibrium potential for that. If it is a standard state, this becomes E naught. If it's not a standard state, it becomes equilibrium potential, right? But this is the potential goes up. And this is, of course, the equilibrium potentials. Okay. Now, what is this equilibrium potential now? This goes in this negative direction. This is relative positive direction. Now, what I'm going to do is I'm now applying. Again, go back. I am drawing this cell here. This is the platinum electrode. Now, this has got. Now, I'm going to apply a current. How do I apply a current? I have a DC source. Okay. And I apply a current here. That means I put electrons here, right? And when electrons are going here, then the reduction reaction occurs. Now, when I apply a potential, the current is increasing. Now, what happens? The current will increase like that when you, like this. Then probably at some time, the current becomes like this. Okay. Now, this is called as activation control, follows the Tafel kinetics. I hope you would have studied there, Tafel kinetics. But please notice, when you increase the over voltage, the current is increasing. Okay. So what does it mean? This is my electrode surface, let's say. Okay. Then you have oxygen in the solution. You have oxygen in solution. Everywhere there is one solution. So when I apply voltage, the oxygen moves from here to this, right? It moves here. Please notice this oxygen has to diffuse in the solution to reach the surface. Now the diffusion depends upon what? J flux is equal to what? Minus D upon DC concentration upon the dx. What is dx? Dx is the diffusion layer thickness, right? So if this has to move, the movement of this depends upon diffusion coefficient, the concentration gradient between the surface and the bulk solution, and then there is a diffusion layer. Now there's a diffusion layer here. What is the meaning of that? Initially, the concentration of oxygen here, the surface are same. When the reaction occurs, the oxygen concentration decreases. And when you're going to increase the voltage more and more, faster reaction occurs. Please see the rate of reaction increases with this. The rate of reaction increases here like this. The oxygen starts moving here. Now, at one stage, the oxygen concentration on the surface becomes zero. What does it mean? The moment oxygen reaches the surface, it immediately gets oxidized. The concentration of surface of oxygen is so zero here. Now, when the concentration is zero, the DC, what is DC? Concentration of oxygen in the bulk minus concentration of oxygen in the solution, right? Now look at this value. This value C bulk minus CS becomes the maximum when the surface concentration becomes zero. When the surface concentration becomes zero, the DC becomes the highest. The flux becomes the highest. What is flux? Flux is nothing but moles, right? Per area and per time, isn't it? So the flux, so again, moles is related to current, right? So when the surface concentration becomes zero, maximum flux can occur. Beyond that, you can't do anything. So when I keep increasing this potential, the current increases. And because why does increases? Because there's a driving force. Please see, you are applying a driving force. Eta is nothing but a driving force. So as the driving force is increasing, the rate of reaction is increasing. But then beyond certain level, everything disappears. Nothing is there on the surface now. Moment it comes, it's done. So if I increase further here and further potentials, nothing happens because surface concentration already reached zero here. Here also zero only. So that means it reaches the maximum current. And now it is 100% controlled by the diffusion process. But this depends upon the D value. That depends upon the bulk concentration. Of course, that depends upon the diffusion layer thickness. So the limiting current is the current that depends upon factors like diffusion coefficient, bulk composition we talk about, then the layer thickness. Now, if you lower the layer thickness, then this also will increase, right? If you become less, how do you lower the thickness? I do agitation, I do stirring. When I do stirring, what happens? This layer becomes close by because the convection, it pushes the oxygen molecule to the surface. So this becomes smaller now. So the limiting current density will increase as you do agitation more and more. Okay. I hope that you have an idea now about what is mean by the limiting current density. So the limiting current density is a condition where the surface concentration of the species to be reduced or oxidized either way, they become zero. Now, mostly we talk about a cathodic. Why? Because the cathodic means these ions coming from a solution. Anodic, we don't talk. Why? At least anodic for metals, we don't talk. Okay? Because the metal surface is rich in metal ions, right? Metal, right? So always there is infinite amount of metal on the surface. And so you don't get the diffusion control for anodic reaction, especially dealing with metal corrosion. Of course, there are other reactions where there can be diffusion control, even anodic also, right? So that's the difference between why you don't get diffusion control in the case of metal corrosion. It only, I mean, anodic corrosion. And why is that diffusion is not controlling the metal oxidation? It only controls the reduction process because of this reason only. Okay, I hope I've answered this. I mean, you understood. If not, please do again send a message. I will try to explain more.
Thank you, sir, for the clarification. We have around 17 minutes left and we have two more
Okay.
questions.
Okay, great.
And one of the question is from Sanjit Dhar. So he has asked, please explain mixed potential theory. What are the factors governing oxidation of metals at high temperature? How does inclusion shape affects the corrosion rate? What are the major corrosion problems in iron and steel industries? So it's a 4-part question. It's a very big question.
Yeah, okay. Sandeep, yeah, thank you very much. A very, very interesting question. You just closely observe what is the meaning of mixed potential. It is mixed potential. It is neither, see, for corrosion to occur, there is an oxidation of the metal and reduction of the other species, right? So suppose I am having, let's say, iron. Take your own example here. Okay, iron, it has a potential, for example, okay, 2 electrons gives you iron. It establishes a potential. If it is standard state, it becomes, I think, minus 0. If I'm not mistaken, there's 44, something like that. I think, okay, somewhere 447 or something like that voltage, right? Standard potentials. Okay. Now, suppose I say acid, you have H plus, okay, plus electron gives you 1 hydrogen, and again it's a standard state. It becomes 0, 0. Okay, is a potential that we talk about. When you immerse, iron in the acid, suppose immerse it now, what happens? Now iron gets oxidized and hydrogen gets liberated. In that case, you don't get this potential, nor you get this particular potentials. You get a potentials dictated by the kinetics of metal oxidation, the kinetics of the hydrogen reduction reaction, right? So that's why it's called mixed potential theory. So I won't draw it very quickly. Suppose I use this Evans diagram, okay? E, and it is my equilibrium potential for hydrogen, goes like that, okay? And this is exchange current density for that. Similarly, I may have for iron, okay? This is equilibrium potential, and this, and this is the exchange current density that I have actually, right? Then it goes like this. Please see that this is the equilibrium potential for the iron, This is equilibrium potential for the H plus, right? H. Now, what happens now? Because they have two different potentials. Now, see, these are the same metal. You have metal oxidation here, equilibrium, and you have hydrogen equilibrium. The metal is now conducting. See, at one place it becomes zero. For example, here 0, 0. Suppose for hydrogen, but iron is going to be minus 0.44. Please see that it may establish two potentials on the same metal surface. The metal surface is conducting now. There's no resistance here. So this voltage will drift. This will drift towards this. This will drift towards this. When this drifts, this follows this kinetics. This follows this kinetics. And at this particular point, it's a very important point, the rate of reduction of hydrogen equal to rate of oxidation of the metal here. And so you get E car and you get I car here. So the mixture potential theory tells you what will be the corrosion potential, what will be the corrosion current density for a given set of reactions, right? Of course, you must know the table slopes, right? You must know the extent current density. You must know the equilibrium potentials. If you know it, you can in fact calculate. You solve the two simultaneous equations and put a condition where the I for this and I for this are same, and E car is same for both. You will be able to solve the equations. You get this at all here. Okay, it's good. Now let me go to high temperature now. In high temperature, oxidation is slightly different from that of the aqueous corrosion. Now, even in aqueous corrosion, for example, iron can get corroded, and finally it can form iron. It can form a hematite. It can form magnetite. But the difference is iron will corrode and form iron hydroxide. Iron hydroxide will convert into ferric hydroxide. Ferric hydroxide will dehydrate and can form a hematite, or you can form hematite plus, or it can be magnetite can form. So the oxide formation in aqueous corrosion is through formation of hydroxide and things like that, and forms oxide there. But in the case of high temperature oxidation, what happens? The gaseous hydrogen directly interacts with the metal, right? Okay, because of high temperature, now iron will directly interact with the oxygen there, and it can form a series of oxides. It can form FeO, can form, for example, Fe2O3, can form Fe2O4, depending on the temperatures and depending upon the partial pressure of oxygen there. Now, the protecting capacity of this oxide is very important. Some oxides are highly conducting. Okay, it can conduct the ions, it can conduct electrons. So if the oxide is highly insulating, it becomes more protective. So then we talk about P-type semiconductors, N-type semiconductors, behaviors, and so which ions are moving and all. So understanding of the conducting behavior of the oxides are very important to see the protecting capacity of this. And there are charge carriers. You determine the charge carriers. Okay, if the charge carriers are more, it oxidizes more. So this is the reason why we talk about the so we have chromium, and so excuse me, the oxide behavior really changes. Now we had another question that we talk about is inclusions, right? Yeah, you have various types of inclusion. You have iron, manganese, manganese sulfide inclusion, for example. The manganese sulfide inclusions are notorious, especially when the manganese sulfide inclusions are longer, stronger, for example. So let's say kiln steel, it forms, if sulfur content is larger and manganese content is also larger, it can form a elongated inclusions that lowers the transverse ductility. It also promotes what is called as hydrogen blistering. Okay, so these inclusions are not very good. Apart from these inclusions, you may have silicates, you may have, aluminum oxide, you use silicon oxide can form. So these are also inclusions which can affect the mechanical properties. More importantly, from corrosion point of view, the manganese sulfide inclusions in the elongated ones just are not good at all. There are some kind of NACE or AMPP standards that qualifies a given material for sword gas applications now. Okay, I hope I have answered these questions. If you still have, please do let me know now. Suppose you run short of it, please email me. I'll be very happy to answer you. Yeah, thank you. Can you go to the next question?
Yes, sir. Vilas asks, can you please share any reference to help me solve problems that are similar to the assignment ones.
Let us see. See, what happens is these are. That's a good. I mean, I understand everything. See, these are the problems which we develop. I think probably we'll try to see that we can try to upload some solved problems and do that. But again, what I do normally teach in even IIT also, when we solve the problem, we don't ask a question of same kind where you substitute and again get an answer. Okay, you understood? So we don't give, because that is not the learning process. So when we give a worked-out examples, the worked-out examples are primarily given not just to solve the problem, it is just to understand the concept. Okay, so it's understanding of the concept only. Okay, so if you look at from that point of view, yeah, it may give you some training, no doubt about it. But you notice that the problems that I'll give would be of a different kind than the problem given assignment, because these assignments are make you to think so that you understand the concept. If you don't understand the concepts, then this problem cannot be solved. So it is not that there is a standard format of the problem wherein you can plug in, okay, and get the data. But that anybody can do, right? You can write a computer algorithm and keep on feeding data. So the purpose of giving the assignments are primarily to test you if you really understand the concept, not your ability to do a numerical solution problems. Okay, I hope you understand. But still, I think we'll try to see how we can have some few problems for you. Yeah, thank you.
Yes, sir. Just to add on to what you have said, point number one is there is one solved problem set coming up in the next week, like in this week. And one more thing is in lecture one, there are a few suggested readings by the professor. It's around, the timestamp is around lecture one of 56 minutes and 20 seconds. So there is a list of books that can help you to understand the concepts better. So I hope that helps also.
That's nice one, Keith. Good point. Any other questions?
So yes, we have covered all the questions, both on YouTube and in the sheet that we have got.
It's very nice. In fact, initially I was feeling that what is not, we are not really having interactive one. In fact, it is very nice, and the questions are brilliant questions, certainly. And I do hope that you did understood the solutions. The idea is to get a perspective. It's not just finding a solution. That is not the whole idea. The idea is to get a perspective of science involved. You take it from me, you are not going to solve same corrosion problem forever, because corrosion problems are going to be different. But the scientific understanding of corrosion, okay, helps you to solve the variety of problems. Okay, so that should be the overall motive. And of course, it's a struggle. You need to read and understand it all. But once you do it, you become an expert. And okay, and you don't need books after that, right? You can write your own problems and you can ask other people to solve it, actually. Okay, so thanks very much for you people posting a very nice questions, and also thanks Kirtika for very nicely managing this live session. It's wonderful, and also I wish you people very excellent learning process. And again, as I've been telling you, you can always send the questions even when you are going through these lectures, and we'll be happy to respond to you. Okay, thank you.
Thank you, sir. Just to answer Vilas's comment, like he's asking for your email ID. to ask any further questions.
Yeah. Well, I thought it's there already in
It
the
is,
slide, but I can.
yes, it is already accessible through the course portal where you
Yeah.
can email the
My email ID is VS Raja, or I can. Oh, if I put a chat box, it will go to them. You don't go.
I'll just share it, sir. I'm
Okay.
sharing both your
Yeah.
ID and the course ID in case they want to catch us up.
VS Raja.
But it is always available at the portal. You can always ask a question, or you can also start a discussion. The students can start a discussion. So we will be monitoring it so we can also answer if it is not being solved.
Yeah, in fact, it'd be wonderful to pose a question to the community, right? Because there are some people who are shy, they don't want to ask questions. If you ask questions, if the answers are there, they'll also get benefited. And apart from that, it's also possible some of them may be knowing they would like to answer it, right? So we'll be happy if you send questions separately to us. But we'll also address same questions if you are put them in the group. Okay, so we can either way address your questions. Okay, so it's very nice today's session. I really enjoyed, and wish you people again happy learning. And again, thanks Kirtika for very nicely arranging this live session.
Thank you, sir. Thank you for your time.
Thank you very much. Okay. All done? Still live now? No.
We are live, but they are just stopping it now. Yeah. So you can leave the meeting. They'll stop it.
Okay, good. Yeah. So how are you? If it's not live, I will just talk.
No, sir. It
Is it
is
live
live.
still?
It is
Okay.
live.